Prime numbers, they're like the atoms of arithmetic, right? The basic building blocks for all other numbers. But where they show up, well, that's been one of the biggest unsolved mysteries in the history of math. It seems like there's just no rhyme or reason to it. So today, we're going to open the case file on this epic detective story and follow the clues.
And this is really the heart of the mystery, the question that's kept mathematicians up at night for centuries. Are primes truly random? Or is there some kind of hidden pattern, a secret law that tells them where to go? Let's take a look at the evidence.
So here we go. Just the first few numbers in a line. The primes are highlighted. You see 2 and 3, they're right next to each other. Then there's a gap. Then 5 and 7 are pretty close. But after that, the gaps just seem to get wider, more unpredictable. It honestly looks like a random mess, right? A scattering of clues with no obvious pattern at all. Our investigation kicks off way back in ancient Greece, with the very first detective on this case, the one and only, the legendary mathematician Euclid.
Now, what's just incredible is that over 2,000 years ago, Euclid gave us our first monumental breakthrough. He proved with this beautiful, elegant logic that the list of prime numbers is infinite. It never ever ends. And this was a huge lead. It meant our detectives had an infinite list of suspects to investigate. But, it also kind of deepened the mystery. If the list is endless, where's the order?
So Euclid told us that they go on forever, but he didn't tell us how often they pop up. And this new question about the frequency, or you could say the density of primes, well, that would stump the world's greatest minds for the next 2,000 years.
Okay, let's jump forward in time, way forward. We're now in the 1700s, and our next key investigator, Leonhard Euler, enters the scene. He basically picked up this very, very cold case and found the first real clue about how often primes actually show up.
And this really shows you what an incredible leap Euler made. He took the investigation from a simple fact, there are infinitely many, to something much deeper, a quantitative idea. He found a really clever way to measure just how many there are.
So, to get what he did, let's first look at this series right here. We're adding up an infinite number of things. 1 plus a quarter plus a ninth, a 16th, and on and on. Now you might think, hey, if I add an infinite number of terms, the sum has to be infinite, right?
But it's not. In this amazing piece of math, Euler himself proved that this infinite sum actually adds up to a very specific, finite number, pi squared over 6, which is about 1.645. Basically, the terms you're adding get small so fast that the total never blows up. Okay, so what happens if you try the same trick, but you only use the prime numbers? 1/2 plus 1/3 plus 1/5, 1/7, and on, forever. Does this also add up to a nice, neat little number? That's the question Euler decided to tackle.
And the answer? A resounding no. Euler proved this sum just keeps growing forever, all the way to infinity. And this is the key takeaway. Even though primes get rarer the higher you go, they don't get rare fast enough. They are way more common, much denser in the number line than something like the perfect squares. This was the very first hint of a hidden law.
Now, Euler's work was a huge clue, but it wasn't a precise formula. For that, we turn to the next phase of our investigation, where a couple of brilliant mathematicians, Carl Friedrich Gauss and Adrien Marie Legendre, took a totally different approach. They just started counting the primes and looking at the data.
So as a teenager, back in the 1790s, Gauss had this incredible flash of insight. He was just poring over these long tables of prime numbers, and he noticed something. The density of primes, how often they appear around some big number x, seemed to follow a simple rule. It was about 1 over the natural logarithm of x. And from that idea, he came up with this function to estimate the total number of primes that was just uncannily accurate.
I mean, just look at how stunningly accurate his guess was. Take the number of primes up to 1 million. There are exactly 78,498 of them. Gauss's formula? It predicted 78,628. That's an error of less than 0.2%. The data was just overwhelming. This could not be a coincidence. But a guess, no matter how good it is, isn't a proof.
Okay, now let's jump to the 1850s. It's time to meet our next detective, the Russian mathematician Pafnutij Chebyshev. He's the one who took these brilliant guesses and started to build the first solid, provable case.
Chebyshev was meticulous. First, he proved that the true number of primes is always trapped, or squeezed, inside this narrow band around the formula x divided by log x. He basically put mathematical handcuffs on the answer. Second, he shot down a rival theory. He proved a different formula proposed by Legendre was just plain wrong. And third, and this is the big one, he proved that if the ratio of primes to x over log x settles down to a single number, that number absolutely has to be 1.
So here's the thing. Chebyshev got agonizingly close. He proved that if a solution exists, it has to be the one Gauss predicted. But he couldn't prove that last critical piece, that the limit actually does exist. It was like the case was all but solved, but that final conclusive proof was still missing.
And that sets the stage perfectly for the year 1859, a huge year in our story. After centuries of work, the entire mathematical community was standing right on the brink of a solution. So let's recap the case file.
Man, this investigation had been a long, slow burn. From Euclid's discovery of infinity to Euler's insight on density, then Gauss's amazing guess from the data, and finally Chebyshev's rigorous groundwork. Each detective built on the work of the last, slowly closing in on the truth.
So by 1859, the case file was pretty clear. The number one suspect was Gauss's formula. The evidence was it was overwhelming. But they were still missing that one final piece, a totally rigorous proof to close the case for good. And without that, the great prime number mystery remained unsolved.
The tools they had just weren't powerful enough to finish the job. A completely new idea was needed. And it would come from a revolutionary paper in 1859 that connected the very real world of prime numbers to the strange and abstract world of complex and imaginary numbers. But that is a story for another time.